Okay, good morning. So we continue the lesson, but I realized that we will not be able to cover everything for the exam, so there will be one part left. So the exam will be until the end of today's lesson. There will be another part in this chapter that I will not be able to cover uh, for the exam, okay? And then I will cover it after the exam. Okay, so and then I will need to think which exercises from blue pages I have to drop. I will think about them and I will write a list for you. Okay, so the exam will be until the end of this lesson today. So as you see, actually today we want to talk about the graph of the other famous trigonometric function. We talked about the graph of sine and cosine functions. We also need now to talk about the graph of the tangent function. So the graph of the tangent function is a little bit more technical, and the reason is clear because tangent is sine divided by cosine. It is a fraction, and whenever I have zero in the denominator, I will face a little bit of problems. Yeah, so that should be understandable. That's a little bit more complicated than that. And of course, if you remember about sine and cosine, the period for both of them were 360 degrees equivalent to 2 pi. So we just draw the graph of them in one period. And I just told you that if you know the graph of a periodic function in only one single period, you take it and copy and paste it over and over again for both sides, and you get the graph of the full function. Yes. So, but do you remember what was the period of the tangent function? So in the trigonometric equations when we were studying, we usually add n times 360 degrees to sine and cosine functions, yes? But we added something else for tangent, yes?
It was 180 degrees.
It's 100. So it is the period of tangent function is 180 degrees. Okay, so in principle, if I want to draw the graph of this function, because this function is periodic with period 180 degrees, if I can manage to draw the graph of this function in that period, then I take that part and copy and paste it over and over again, then I will generate the graph of the whole function. Okay? But let us see that the function tangent is sine over cosine. So this function is not defined. Tangent x is not defined if the denominator becomes 0. Because if the denominator becomes 0, I am dividing by 0, which is forbidden. Okay, but when cosine becomes 0, you know that, yes? So cosine, this is assuming this is the unit circle. Cosine is related to the x-coordinate. So if you want to have the x-coordinate to be 0, there are 2 points, either here or there. These are the only 2 points on the unit circle whose x-coordinates are 0. Okay, but how can I write all of them? X is equal to, this is 90 degrees, so let me write everything in radians. So it is pi over 2, and another one is minus pi over 2, or equivalently you can say 3 pi over 2. It depends in which direction you want to move. Okay, so if you don't mind, let me just write 3 pi over 2. So I need to consider all those points. So I hope that you agree that I can write pi over 2. If I write 2n pi, it means that I go one full round and I will reach back to the same point. But if I just add n pi instead of 2n pi, then I start from pi over 2, I add pi, and I reach to the other point. When I add pi, I reach this point again. That is, these numbers are not allowed for tangent. Because if you choose any one of these numbers, then the denominator vanishes and the tangent is not defined. So n belongs to 0. So if x is one of these angles, then the tangent is not defined. So it should be something else. But the point is that usually, do you remember when the sine function, the period was 360 degrees, I started drawing the graph from 0 degrees to 360 degrees. Here, the period is 180 degrees. You might think it's a good idea to draw it from 0 to 180 degrees. I'm not saying it is wrong, but it is not the standard convention. Why is that, do you think? So let me repeat the question again. In principle, the period of the function is 180. So it doesn't matter which interval I am taking. As far as that interval has length equal to 180 degrees, that will work. Naturally, you might think that it is better to draw the graph of this function on the interval from 0 to 180 degrees. It is not wrong, but I think there is a good reason if we do not choose this interval. Why is that? Because this interval contains 90 degrees, and 90 degrees is one of those angles where the function is not defined there. Yes? Okay, so what should I do? I would prefer to draw the graph on this interval, minus 90 degrees to 90 degrees. If I ask you what the length is still 180 degrees. Okay? On the other hand, 90 degrees and minus 90 degrees are not acceptable. So I have to take them off, because at 90 and minus 90, the function is not defined. Yes? So this is the natural interval to work for tangent. Because first of all, the length is 180 degrees, which is exactly equal to the period. On the other hand, it does not contain any problematic point, because problematic points are the points that lie either here or there, but I am not on any one of them, so that's a good thing to start. Okay, another thing that I want you to understand, this is written in the book, so this is why I actually want to talk about that one as well. So in the unit circle, we had only two axes, one x-axis, which plays the role of cosine axis, and the other one, the vertical axis, which plays the role of the sine axis. But the book has also introduced another axis, which is called the tangent axis. And this is unique. I just want to teach this part, and then I want to tell you how we can use that to help us to help ourselves to actually draw the graph of this one in a better way. Okay, or at least understand the behavior of the function tangent in a better way. So let me just start from here. So do you remember I have a unit circle? In the unit circle, I have a horizontal axis, x-axis, which plays the role of the cosine. And then I have also a vertical axis, which plays the role of the sine. Okay, now what we introduce is another axis. So let me draw it a little bit more carefully. So here I take this point and then I draw a tangent line to this unit circle exactly at that point. Yes? So here I have this line, but this will continue forever from both sides as usual, and I will take this, which I call point A, as the origin of this new axis. Okay, this axis that I just drew is called the tangent axis. Okay, so let us see how this could be helpful for our purpose. So this is the origin of the red axis. Okay, so the origin of the black axis are these 2 points, yes? Here, So this is the origin of the y-axis and the origin of the x-axis. By convention, we choose this point as the origin of the red axis, which I call the tangent axis. Now consider an angle theta. Okay, so this is an angle theta. If I ask you about the cosine of this angle, you will look at the end point and then read the x-coordinate. So from here to here, if I ask you what is that, that is exactly equal to cosine theta. And if I do the projection on the y-axis, if I ask you what is this length, you would say this is the y-coordinate of this point, so that is nothing except sine theta. What we want to show is that if I continue the second arm of the angle, which is this line, so that it intersects the red axis that I just drew. For example, I continue this, and then I have this intersection point. What I claim is that this is tangent of theta. Okay, so I want to show that this is tangent of theta. So that's my question mark. So we already know how to find sine and cosine. You just find the end point and read the x-coordinate, which is cosine, read the y-coordinate, which is sine. Now I am telling you something new today. I'm saying that if you continue the second arm of this angle in a way that it intersects the new red axis. Of course, there is no point for continuing it from this side. This will never intersect the red axis. So I will continue it from that one. When I found the intersection point, this is called this is the tangent. This is my claim. Still, we don't know why. So let me call this point, for example, point M, and let me give this also a name, point N. What I am telling you is that this algebraic value, this is important to understand. I'm not talking about the length. Here, the length is exactly equal to the average algebraic value. But if this is not on the positive part, if it is in the negative part, then you have to read it as a negative value. But in this case, I'm claiming that this is exactly equal to tangent of theta. So how should we convince ourselves that this is true? Using similarity of triangles. Yes, let me concentrate on two triangles. One triangle, so let me also give here a name. So let me call it B. If you consider this triangle OBN, and the triangle OAM, these two triangles are similar. Why is that? Because two angles from one of them are equal to two angles from the other one. It is easy to see. This angle theta that you see is an angle for this smaller triangle as well as the bigger one. So theta is an angle in common. The other one, hopefully you see that this angle is 90 degrees. This angle is also 90 because the red axis is tangent to the circle. So these two also are equal. So this means that this is true. These two triangles are actually similar. If they are similar, I can write the equality of the corresponding ratios. For example, I can take OB divided by OA. This will be the same if I take BN and then divide it by AM. Because these two triangles are similar, it means corresponding ratios are also equal. Yes, is that clear? Okay, but now let us look. OB in this figure is nothing except cosine theta. If I ask you what is OA, what is OA? What is OA in this picture? What? What? No, OA.
Cosine theta plus BA.
No, yes, that is clear. But OA is the radius of the unit circle, yes? Yes?
So yeah, it's 1.
It's 1, yes. I don't know where you are you leaving, yes? Are you in the class or not?
No.
Okay. So, what is Bn? Bn and this length are equal. So Bn is sine theta. I still don't know Am. You see, it's question mark. My claim is that Am is tangent. But then I hope that you agree that Am is tangent. Why? Because I multiply cosine theta by Am. This becomes this multiplied by that, which is sine theta. And then what I am looking for is Am. Am is sine theta over cosine theta. But we already know what is sine over cosine. It is tangent. So actually that claim is now proven, yes? Is that clear?
Yes.
Okay, so now let us to play around with this concept a little bit so that you can understand that. For example, can you answer the question, what is tangent of 0 degrees? Of course, you already know that. You don't need this new piece of lesson to be able to answer that. If I ask you what is tangent of 0 degrees, so you say that, okay, this is equal to sine of 0 and then cosine 0. I mean, for answering this question, you really don't need this one. The reason that I'm asking you to do it in this way, because I want you to learn how to use this new concept. So sine of 0 is how much? Is 0. Why? Because 0 degrees is this line again. The second arm is here, so the final point is A. The x coordinate is 1, the y coordinate is 0. So this is 0 and this is 1. If I divide them, that becomes 0. So that is the way that we did it in the previous lessons. But now can you tell me how can I understand this very simply using this idea? Because I just told you, whenever you have an angle, if you want to find the tangent of that angle, you just continue this arm in a way that it intersects the tangent axis. And then when you found the point, you read the distance from here to here. If it is above, you take that distance with the positive sign. If it is below, you take the same distance but with the negative sign. Yes? Okay, now, can you tell me what is tangent of 0 in this picture, in this method, in this way of thinking? Yes? Yeah?
It's 0 because it's straight, it's going to intersect.
Exactly, because that is the 0. When I continue it from this side, there is no hope to continue having an intersection, so I continue in that way, but it exactly intersects at the point A. So the distance from the intersection point, which is A, to the origin, which is coincidentally A in this case, is nothing, is 0, so tangent of 0 is 0. For example, can you tell me what is tangent of 180 degrees in this setup? Of course, again, you can answer this question like that, but let us answer it here. So where is 180 degrees? So let me just draw. So 180 degrees is coming from here, okay? So this is the second arm of the angle 180 degrees. I am supposed to continue this, I am supposed to extend this in a way that I have the intersection point. If I extend it in that direction, there is no intersection points. I extend it in that direction. Where will be the intersection point again? A. And so the tangent of 180 degrees according to this new setup is again 0, which is correct. So that is 0. Let us understand tangent of 90 degrees. You already answered that. What is tangent of 90 degrees? Is not defined. Why tangent of 90 degrees not defined in this case as well? Yes?
There are no intersections.
Yes, because 90 degrees is here. So this is the second leg of 90 degrees. When I continue it in any directions, it doesn't matter. I will not be able to intersect this because they are parallel. Yes? This means that there are no intersection points, so the tangent is not defined. Or we can say that they intersect at, because sometimes people say that two parallel lines intersect at infinity. Yes? That's also, I don't know, have you heard about this or not? So the intersection point, because if they are not exactly parallel, for example, assume that this one of them is 90, the other one is 8999, yes, for example. They are not, of course, parallel. They will intersect, but very, very far away. This is why people say that if you have two parallel lines, they intersect at infinity. That's the idea. So this is why also it is understandable to say the limit of the tangent x when x approaches 90 degrees. So let me write in radians. It's plus infinity. But of course, it should be from the right-hand side. Sorry, left-hand side. It means that it should be smaller than 90 degrees. So if you start increasing the values of x, making them closer and closer to pi over 2, but being always smaller than pi over 2, what you expect that the values for tangent increases without any bonds. Yes, that is also very easily to detect in this picture, which was not that before. So what I do, so assume that this is my angle, the intersection is here. Let me increase the angle a little bit, so hopefully you see what is happening. The intersection will go a little bit further, yes? It will be farther away from A. And if I increase this a little bit more, you see the values are actually increasing. So if I get closer and closer to 90, I hope that you immediately agree that this distance between this point and the intersection point will increase. Okay? So when I am very, very close to 90, what will happen? This intersection point will be very, very far away from the origin. And it is extreme. If I am extremely, extremely close to 90 degrees, that would be extremely, extremely big, that intersection point. Yes, it would be very, very far away. So this is why it's a good way of understanding this tangent of x, limit of tangent of x, when x approaches pi over 2, but from the left-hand side. Don't think that this is the right-hand side. I'm talking about on the x-axis. So if this is the x-axis, here is pi over 2. I want to approach to pi over 2 from smaller values. Smaller values on this picture seems to be on the right-hand side. But what I care is the axis, okay? Okay, now can you answer this question? Because that's also important. So the limit of tangent of x approaches to pi over 2, but from bigger values. So do you remember? I don't know how much you remember from Math 3C lesson. So if we have limits, these signs that I am putting here are not negative and positive signs. So x approaches pi over 2. This means from the left-hand side. So if this is pi over 2, x approaches pi over 2 with this negative on top. It means that I am getting closer and closer to pi over 2 from the left-hand side. This means that I am getting closer and closer to pi over 2, but from the right-hand side. That positive and negative sign on top means left or right, okay? Okay, now can you tell me what is the answer to this new limit? So I realized when I am getting closer and closer to pi over 2 from smaller values of x, then this length is actually increasing and increasing in the positive direction. But now let us see what happens if I get closer and closer to the same value, but this time with bigger angles, bigger than pi over 2. For example, assume that I am here. Let me make a little bit more exaggeration. So assume that first I am here. This is my angle. If I ask you where the tangent is, how should I understand that? I have to continue the second arm. There is no point of continuing in this direction because I will not have an intersection point. So I will continue in that direction. That would be my intersection point. By the way, tangent of this angle is positive or negative according to this picture? Is it positive or negative? Negative, because the intersection point is below the origin. Okay? Okay, but now let us see what happens. I want to become closer to pi over 2, but from this direction. So if I am getting closer, then what happens to the tangent value? It goes lower. And then I go a little bit closer, and then you see the intersection point will be even lower. So what is your intuition? If I am becoming extremely close to pi over 2, then what will happen?
It approaches negative infinity.
It approaches negative infinity. Okay, so this means that the limit is negative infinity. It's good to see. So you see, this is a very nice picture. You can imagine what is happening to tangent at the different borders. Any questions here? Another thing that happens, because I am interested on this interval now from minus 90 to 90, so for example, you realize that in one period, the tangent function, the sine and cosine function actually are going up and down. For example, sine function goes up to here, and then turns back and goes down up to here, then again it starts going up. So it is increasing here and here, and it is decreasing here. Okay? Do you think the same thing will happen for tangent in one period, not any period, on this period? Do you think this will happen for tangent as well? That the tangent will go up and down, or it will continuously go up or continuously goes down? This is clear from the picture. No ideas? So one thing is clear. If I am on the first quadrant between 0 and 90, rather between minus 90 and 90. So for example, let us be between 0 and 90. What is the behavior of tangent? Do you think tangent goes up and down or continuously increases? So you are here, tangent is 0. You start increasing the angle, but still you are in the first quadrant. What is happening to the values of the tangent? Yes? They are increasing. So that is clear. Okay, now I want to do the same thing, but I want to expand my interval from minus 90 to 90. What happens to the value of the tangent? Are they always increasing or not? Again, because at that point on the first quadrant, this is increasing all the time. But what happens if I expand my interval from minus 90 to 90?
It also decreases.
Decreases?
Yes.
No, because I am going from minus 90. Be careful, increasing and decreasing are conventional. So we always go to the right.
So it's always increasing.
It's always increasing because if I have at minus 90, no intersection point, where I am at minus infinity, okay? If I start increasing the angle, I want to go from 90 to 90 and I want to understand the behavior of the tangent. So you see, first of all, it is minus infinity when I am here. As soon as I just rotate a little bit, it becomes an extremely negative value. When I increase that, this negative value is actually shrinking. When the negative value is shrinking, it means the function is increasing because it is less negative now. Yes, you start from a very negative value and you're becoming less and less negative. So it means that you are increasing in value. Yes, and then I increase from negative values, then I reach to 0, then I still continue and increasing. So it means all the time you are increasing, but increasing from minus infinity up to positive infinity. That's the behavior. So you shouldn't expect up and downs for tangent. The tangent function is always and always increasing on this interval. Yes? But then what happens after that? Assume that I start increasing. I am at minus infinity, hypothetically, and then I increase, and I reach to positive infinity. But let us assume that I still continue. What will happen? Here, so you see here, minus infinity. I increase, I reach here, I go to positive infinity. Then a slight change, what will happen?
It will start
It jumps to negative infinity once more. Yes, so this you understand there is one behavior is going on that is not continuous. Yes, because I was actually in the heaven and 1 second later I am in the hell. Yes, so this behavior is actually not happening when you are doing something continuous. It means that something satanic is going there. Yes, so something has happened, and that is that the graph is breaking down. Okay, so that is the behavior I want you to understand from here. And of course, Another thing we want to do is just to understand how to draw the graph of the function in this period by doing some numbers at the end. Because drawing qualitatively, we need to know more about derivatives. Okay? Okay, so what I do, I will set up a table of values from minus 90 degrees to 90 degrees, and then the middle one is 0. Another famous angle that we know in the middle, which is easy to draw, is 45, because tangent of 45, if you remember, is how much? Is 1. By the way, what is tangent of 45 degrees in this picture? It is very messy, but let us understand. If it is going to be 45, it is the angle bisector here. Okay, so this is a very, very bad picture, so it's more confusing than... I mean, if this is 45 degrees, I hope that you agree with me, this will be a unit square here, if this is 45. So this means that this length is equal to this length. And this length is 1, so this is also 1. So this is why tangent of 45 degrees is 1 from this picture. Anyway, it doesn't matter here that much. So here I have x, here I have tangent. Of course, I have other famous angles, but drawing them on the picture is not that easy. But 45 is very handy. So here it is undefined. It's undefined. Here it is undefined. And here, 0 degrees, tangent of 0 degrees is 0, tangent of minus 45 is minus 1, tangent of 45 is 1. But this is undefined, but goes to negative infinity. This is undefined, but it goes to positive infinity. Okay, and then if I want to draw the graph, not draw, sketching just the graph. So, minus 90, so let us assume that here is minus 90. And then let us assume that here is minus 45. And then here is of course 0, and then I have here to be 45. And here I have 90. At minus 90 and 90 degrees, I have problems. Usually, of course, GeoGebra doesn't draw these extra lines, but I prefer to draw them with dashed lines. So to advocate that the tangent is not defined here. And it is not defined here either. We will study these lines later. These are called asymptotes. Asymptotes. Okay. Okay, then we know that when I am on the right hand side of minus 90 degrees, I am in the hell, yes, minus infinity. So then I am here, so I am very, very down, yes. And then when it comes to minus 45, it is minus 1. So that's 1 point. When it comes to 0, it is 0. When it comes to 45, it is exactly 1. So 1 minus 1. And then when I reached suddenly close to 90, I go actually up and up. Yes, so it's something here. So then the behavior of the function is something like this. And as we predict, I'm actually respecting this function is always and always continuous. And it is not continuous on this interval, and actually it is always increasing. That's the idea. But then what happens? You have to copy and paste this graph over and over again. So what happens if I take this graph and put it next to it? So this, I will put it here, then I will draw this line. It's 90, it's 270 now here. And then what happens, you will have another, so this should be solid lines. All these solid lines are actually part of the graph of the whole function. Okay, and I have to repeat it here as well, yes, you see. So I get infinitely many branches. And then you see that what is happening. On the left hand side of 90 degrees, very close to it, I am on top. And a little bit to the right, I suddenly go down, yes? So that's the behavior that we were able to predict using that idea. Any questions? Okay. So let us actually go here. So that was what we actually learned. So, but in the book, they have also put more points in the middle. Of course, I skipped those, but you see that this will happen. And they are trying to convince you about what is happening using this diagram as well. I think it's a good idea if we go to GeoGebra here as well, and to see how we can draw the graph. Okay, so I will first get rid of these extra lines here. Oops, it is not functioning. Okay, so let me just get rid of these. Yes, that's good. And then let me change this x-axis to distance. I will choose, I think pi over 2 is, I think pi over 4 is better, yes. I will do it pi over 4, and then we have this, and then let me a little bit zoom in. And that's good, I think. And then we go here and type tangent, and it's automatically it is in radians in GeoGebra. I don't know, so I have to respect even though it worked. Okay, so this is the graph that you get, which is actually this one, and you see those dotted lines are absent here, and that's correct because dotted lines are actually the dotted lines are actually not part of the graph of this function. We draw them for guiding us how to draw them, okay, somehow. So this is called an asymptote. I will come back to it later. But here you see that I have this scenario. That's more or less, so if I actually start zooming out, you see that I have these branches coming in one after the other. So it shows that the function is periodic, but the period is that part that you just copy and paste it. But it's hopefully easy for you to understand what is going on. Any questions? Okay, so remember this way, this graph is also something famous that you need to know, like sine and cosine functions. Okay, but another question in the book that you see, let me also talk a little bit about that, and the lesson today is finished. So let me solve this example, at least one part of it. For which value or values for x, these functions are not defined. Okay, so this is one example that you need to know. For example, let me just solve part B. Okay, we want to choose those values for x so that the function tangent 3x is not defined. Yes? Okay, so what we do, so can you help me to do this? I want to find those values for x so that tangent 3x is not defined. So how should I solve that question? Yes?
You should make 3x into 90 or minus 90.
Not just, no, because this is not wrong, but this is not the complete version. More than that, because you saw that there are infinitely many discontinuities. So you should solve it in this way. You need to write this as what? Sine over cosine of the same angle. But then you say that this tangent is not defined if and only if the denominator vanishes. So this means that you put this to 0 yourself. It means that if this is happening, this is not defined. And then I don't just remind you about the formulas that we had. So if we have cosine of a box equals to 0, what is inside the box? The box is equal to a pi over 2 plus n pi. We just learned that because cosine is supposed to be 0, it means the x coordinate should be 0. So either I am here or there. So if I want to combine these two in one single formula, instead of writing 2n pi, I just write n pi. So that's it. But here, this is playing the role of your box. So this means that 3x should be pi over 2, but plus n pi, where n is an integer. But you are looking for x, so you divide everything by 3, so this becomes pi over 6, and then the other one becomes n pi over 3. And n belongs to z. So that is the answer that you have to provide for this problem. Yes? Okay, any questions? Okay, so as I told you that the exam will be until the end of this lesson. So there's one part left that needs teaching. The other part is the application of trigonometry. Nothing there is. Of course, it is very important. I need to solve some problems for you to see how this will act. That is actually the application of trigonometry in real life. Yes, I mean real life means science here. Okay, so in that case, it is important. Okay, any questions? Okay, thank you.